So we've covered some of these options here for substitutional atoms, and we've seen that we can generate vacancies here just by arguments for occupying lattice sites and maintaining electroneutrality and generating some vacancies by that. And we'll touch on now some interstitial atoms as an option. We saw moments ago that we can create vacancies in a lattice. So here's one type. And an interstitial site, we saw that earlier. So this is where an atom might be small enough to fit nicely into an interstitial site in the host material. So there's an interstitial site, and if we can position something there, that would be a defect. Now these can occur for a variety of reasons. Like we saw in the case of carbon, it's small enough. Temperature can affect this too, as well as other kind of ionic charge requirements. Okay, so we've seen these two being very common defects so far. The vacancy, where we are missing an atom, and these interstitial defects as well. Depicted for you a little more differently and more obviously here. Here you can see the influences of a vacancy site on the bonding. So when an atom is missing, as you might expect, the neighboring atoms might take advantage of that space a little bit. And so this allows relaxation into the void space, into the vacancy, and we can have some extension of bonds between these atom sites. Okay, so these bonds that I'm drawing here are a little bit longer than those that are well away from that vacancy site. Okay, so we'll see distortion of the planes of atoms near that vacancy site. And this becomes an important stress concentrator for when we talk about mechanical properties and ultimate failure of materials. How about interstitial sites? Looking at that with a little bit more of a detailed view of the planes that nearing that site. As you can see here, bonds are again asked to distort and stretch. So here these bonds are very long to now accommodate the additional interstitial atom of the same type. So this self-interstitial, same atom type going into its interstitial position, is forcing bonds to stretch very far from one another. And again, those would be the ones that are positioned most close to our axes that we've seen before for bond breakage. Okay, so if we're positioning atoms to be further from one another on the r-axis here, then the midpoint of these graphs, we are much closer to the x-axis, and the energy to ultimately break the bond is lower. So these bonds are favored for breaking because of the self-interstitial in this diagram. Okay. Okay, so we can actually quantify some of these vacancies. So looking at the opportunity to simply have one of these sites eliminated, we can quantify that according to the energy it takes to displace that atom out of its lattice site. So this is called an activation energy. And in many equations, this is given value QV, the energy Q to create the vacancy. Okay. Often this is reported in energy units like the electron volt per site, so per atom, for example. Okay. This is normalized, divided through by a constant, the Boltzmann constant. So it becomes imperative to use a Boltzmann constant that matches values of the activation energy provided. Okay, so we have two options there. We have the version in joules or the version in electron volts, and an earlier lecture showed you how to transform between the two. Okay, so that's the denominator of the parenthetical piece of this equation. And the final piece of the denominator is temperature in Kelvin. Okay, so there you can see the denominator piece has a temperature parameter. So notice this equation is exponential. So we have the fact that the ratio of defects, vacancies, to the total number of sites, so that might be every white sphere down here, and the number of vacancies might be that one position here, so that's a V vacancy. And then all of these options here are atom sites, so total number of atom sites is our denominator. And this is exponential. So in other words, written differently, it's e to the power of this parenthetical statement, Q over KT. So the proportion of vacancies relative to the total number of sites goes exponentially and is reflected here. So the larger the temperature, the more negative the exponent is here. The larger the temperature, the smaller the exponent here is, the larger we can make the value, the ultimate ratio. And so we will program for more vacancies, as you might expect. Provide thermal energy, provide temperature, we will gain more empty sites in the lattice. Okay, so if you can imagine the outcome there, plotting the left-hand side of that equation versus temperature, you can see here that we would get an exponential curve as a consequence. Okay, so increase the temperature, and you'll get an exponential increase in the amount of vacancies relative to the total options available. Okay. So how we handle this equation is certainly the left-hand side is total number of sites, if you haven't heard me say it. It is the total number of atoms under consideration. So if we can use density equations and the mass of a material in question, we can count the total number of atoms, and we can use that to determine the total number of sites in question. And then with knowledge for the energy required to create a vacancy, the activation energy, and the temperature, we can predict the total number of vacancies, how many spots will be empty in the lattice. Okay, so let's take a look at that. And think about the two types of vacancies that we have. We have void vacancies, like we just saw, so that equation applies here. And now when we consider self-interstitials, where we're asking the metal to occupy a spot in its own lattice, so to occupy an interstitial spot in its own lattice, you can see how much distortion we have to apply to the planes of atoms to do that. You can think of the consequence on the activation energy to do that. So here, simply asking an atom to be not present in its own lattice is QV. Now, if you want to ask an atom to occupy its own interstitial site, you need to provide 3 times the activation energy for that vacancy site to allow that interstitial option to exist. Okay. And so for that reason, as you can see here, these are much less likely. And note here that we're putting threefold the activation energy in the exponent of our previous equation. And so it has large impacts on the actual number of vacancies that are due to self-interstitials. Those are very, very rare as a consequence. Okay, so here's our equation again. This is simply for vacancies, so missing atoms of metal in our lattice. And let's look at an example here where we're asked to find the number of equilibrium vacancies in 1 meter by 1 meter by 1 meter, so 1 cubic meter of copper at room temperature. Let's see if we can handle this equation. So again, to find the total number of vacancies in this volume of copper, what we want to try to do is transform this into number of atoms. And we know that this is, our assumption is that the total number of atoms is equal to the number of sites. Okay, so that's this value over here. We're provided temperature, So that's room temperature. So we know the purple parameter, therefore. We know the Boltzmann constants, one of those two. We're given the activation energy of 0.9 electron volts per atom. Okay, so that's this value, obviously. And so we have everything to determine the total number of vacancies. So see if you can do that. You will need, of course, Avogadro's number and the density. So the density of copper is 8.4 grams per cubic centimeter. And the atomic mass of copper is shown here. And of course, we have Avogadro's number. So see if you can determine the total number of vacancies in a cubic meter of copper at room temperature by using what's on the screen here. Resume the video once you've had a chance to determine the answer. Okay, so we'll begin this problem by determining the mass of copper using the volume information that we have. So the volume of copper was 1 meter cubed, and we know that 1 meter cubed can be transformed into cubic centimeters, knowing that there are 100 centimeters per meter. And if I cube that, I will cancel the meters cubed information, go into centimeters cubed. And so I will end up with 1 times 10 to the 6 centimeters cubed of copper in question. Okay. Now I can, knowing the density equation, that density of copper is simply the mass of copper divided by the volume of copper. I can solve for mass. So the mass of copper is going to be equal to the 8.4 grams per cubic centimeter times the volume of copper in question. So that is the 1 times 10 to the 6 centimeters cubed. And I now have 8.4 times 10 to the 6 grams of copper that are in question. Taking this through to number of copper atoms is how we get to the number of sites. So I'm going to determine the number of copper atoms by using that 8.4 times 10 to the 6 grams of copper, multiplying by 1 mole divided through by that 63.5 gram value, atomic mass information for copper, and then multiply by Avogadro's number, 6.02 times 10 to the 23 for every 1 mole. And I end up with approximately 8 times 10 to the 28 atoms of copper in this question. Okay, 8.4. I'm sorry, 8 times 10 to the 29. Let me just confirm that. 8.4 E6 divided by 63.5 times 6.022 E23. Oh no, I had it right. Apologies, 28. 8.0 times 10 to the 28 atoms of copper. Okay. So number of vacancies is equal to the number of sites times e to the power of minus qv over kt. Okay, so I had that by moving the denominator ns to the other site. So number of copper atoms was 8 times 10 to the 28. We also know that this is NS. That's our earlier comment. So we have this piece here. Okay, so we'll leave that for now, and we'll focus on the exponent here. So e to the power of minus 0.9 electron volts per atom was the provided activation energy to create a vacancy, divided through by the Boltzmann constant in electron volts per atom per K. And so that value is 8.62 times 10 to the minus 5 electron volts per atom K. And of course we need to multiply that by the temperature, and so the room temperature is about 22 degrees C, and so that correlates to about 300 Kelvin for the value of room temperature. Okay, so we're going to take the NS value and we're going to multiply by E raised to an exponent here. So that exponent will be the consequence of the information in that parentheses, so it's going to be 8.62 exponent 5 negative times 300K okay, and then I'm going to invert that number and multiply it by 0.9 negative. So I will be raising e to the power of negative 34.8028. And the value should be unitless because Kelvin is canceled Kelvin here. Electron volts is canceled electron volts, and per atom is canceled per atom. So raising e to that gives me an S is equal to that times 7.6796 and 7 times 10 to the minus 16. Okay, so almost there. Total number of vacancies, we had the number there, was total number of sites was 8.0 times 10 to the 28 atom sites. Okay, so we'll just call that sites now. Times this very small number, so times 7.6797 times 10 to the minus 16. Unitless. And this tells us that we have roughly 6.1437 times 10 to the (13) sites that are vacant. Okay, so out of 10 to the 28 atom sites, 10 to the 13 are vacant.